Hi all again. Let's continue the lecture that we did last time. We talked about the superposition theorem and Thevenin's theorem. Superposition theorem could be used to find out a voltage or a current in a single branch or an element by considering one source by source in the network rather than performing mesh analysis, nodal analysis or anything like that. And the Thevenin's theorem helped us to convert the circuit, excluding the resistor that we are considering, into a voltage source in series with the resistor, so that we could do any changes to the resistor and check the behavior of the circuit, or basically the voltage or the current of the resistor could be observed by changing making any changes to the resistor value. Today we will start the discussion from the Norton's theorem. Now in the Norton's theorem, instead of converting the circuit into a voltage source, here we convert it into a single current source. Now when it comes to current source, you need to have a parallel resistance instead of a series resistance. So we will be converting the network, excluding that resistor that we are considering, into a current source and a parallel resistor. The Norton's theorem says any linear bilateral network may be reduced to a simplified two-terminal circuit consisting of a single current source and a single shunt resistor, as shown in the figure. So here, instead of a voltage source, we convert the rest of the circuit into a current source with a parallel resistor. So let's look at the steps. Steps are more or less very similar to the steps that we followed with the Thevenin's theorem. First step is the same: remove the load, and then mark the two terminals, and then make all the sources to 0. So up to that point it is the same. Even next step is determine the Norton's equivalent resistance Rn between the two terminals. That is the same in the terminus equivalent case as well, but we label that as Thevenin's resistance. So Thevenin's resistance and Norton resistance are equal to each other. It's the same value. The next step, however, replace all the sources that we did, but what we do is we connect a short circuit between the terminals A and B and try to find the current through that, because when it comes to a voltage source, what we wanted to find is the internal voltage. So measuring open circuit voltage does that, but now we want to find the current. So if you short circuit the Norton's equivalent, like if we say this one, if you create a short circuit in here, that will actually give you the IN value. So for the original circuit, if we do the same thing, we get the IN value. The final step is you actually have to draw the circuit and then do the rest of the work, right? Now if you actually know the Thevenin's equivalent, you can use source conversion that we've been using earlier to convert the Thevenin's equivalent into the Norton's equivalent, or else if you know the Norton's equivalent, you can use the source conversion techniques to find the Thevenin's equivalent. But one of these will have to be found using the two techniques that we discussed. So let's take this example and see how we are going to determine the Norton's equivalent for the circuit given in here. This is the same circuit that we use for the Thevenin's equivalent as well. That would make our life easier. So let's take this circuit. So first step is to let's take the other circuit actually. The first step is to remove the load and label the two terminals as A and B. So let's take this circuit instead. Although I have left space in the PPT, I would like to do it in here. so the steps can be easily seen and clearer. Okay, so what we need to do here is to first remove all the sources in order to find the Thevenin's equivalent. So remove sources. If you remove sources, we will get this circuit. The voltage source will be removed, which is actually a short circuit now, which will become a short circuit, and the current source becomes an open circuit once it is removed, that we discussed last time. So this is my A and B. So when you look into this, this is 24 ohms. Our Norton is 24 ohms. So the first part is done. Now we'll have to take one source by source and find out this is to find out actually Rn, right? To find out Rn, then we will try to find out In. To find out In, consider E only, like what we did last time, but we have a difference in here. Instead of the open circuit voltage, we will have to take the short circuit current. So let's take this. This is not comfortable. Okay. So we have an open circuit here, right? So 24 ohms and 20 volts, and we will have to connect. I'll draw in a different color. Connect a short circuit and find I1. From this circuit, I1 is equal to okay, so 20 volts divided by 24 ohms using Ohm's law, which will be 20 divided by 24, which is 0.83 ohms, rather 0.83 amperes, 0.83 amperes. Now we'll do the same thing with considering I only. We will get a circuit. We have the resistor. Instead of the voltage source, we will have a short, and then we will have the current source. The current source is downwards 2 amperes, and again we'll connect a short circuit here and mark the current like that, I2. Now from this circuit, if you create a short circuit here, because this is 24 ohms resistor, when you create a short circuit, you will get minus I2 is equal to minus 2 amperes. So from these two, using superposition theorem, In is I1 plus I2, which is 0.83 minus 2 amperes, which will be this minus 2, which is minus 1.17, right? It's minus 1.17 amperes. Now the Norton's equivalent is you have a current source and a parallel resistance and the load resistor here. So current is now negative, meaning that your arrow should be like that. So IN is 1.17 amperes, RN is 24 ohms, and RL was 16 ohms, right? 16 ohms. We are supposed to find calculate the current through RL. Current through RL, if you label the current through RL as downwards IL, we can use the current divider rule. E is equal to 24 divided by 24 plus 16 into minus 1.17, which is 1.17 into 24 divided by 24 plus 16 is 40, which is 0.7 amperes. So minus 0.7 amperes. So IL is upwards 0.7 amperes. Right, so that's that. The steps are shown in here anyway. So okay, the solution is this, and you get the values that we discussed in the example. So if you now previously we calculated the Norton's equivalent, the Thévenin's equivalent for the same circuit using source conversion techniques. We can calculate the Norton's equivalent as well from the Thevenin's, or if you calculated the Norton's equivalent first, you can calculate the Thevenin's equivalent using the source conversions. Right, the next is the maximum power transfer theorem. In amplifiers and most other communication circuits, we are concerned about the maximum power transfer to the load under different conditions. Now you have a certain, as you can see here in this, you have a certain characteristic. We call now at this point this as the characteristic impedance when it comes to a amplifier and a communication circuit. That is actually the Thevenin's resistance or the Norton's resistance of the particular circuit, excluding the load. The same thing that we did. So the maximum power transfer theorem says that the load resistance will receive maximum power from a circuit when the resistance of the load is exactly the same as the Thevenin's or Norton's resistance looking back at the circuit. So that does mean that consider these two cases, whether you convert the circuit to a Thevenin's equivalent or to a Norton's equivalent. What the maximum power transfer theorem says is that when RL is exactly equal to RTH or RN in this case, the maximum power will be transferred to the load. So in that case, maximum power transfer occurs when RL is equal to either RTH or RN, both are the same. We saw that earlier. Hence the maximum power delivered to the load would be E squared, in this case the V squared over R. Now V is the voltage here. I'll show that the voltage V at that point is V is equal to at the maximum power transfer, these two are exactly equal to each other, therefore it is ETH by 2. And again in this case both these are equal to each other, so IL is equal to this is equal to IN divided by 2, because it's a current divider with two equal resistors. With that, IL squared will become IN squared over 4 into Rn, so I squared Rn and E squared over RTH. So that will give us the maximum power transfer. The proof of it is, what we have to do is to for at the maximum or the minimum, the derivative becomes equal to 0. So here what we have taken is V squared over R, like what we did earlier. Now earlier what we did was when these two are equal to each other, but now this is the voltage is VL squared, which is equal to RL over RL plus RTH, using voltage divider rule, into ETH. So the whole thing squared is what is written in here, right? So RL into ETH, RL plus RTH, whole thing squared. So that becomes simplified like this, and what you need to do is to take the first derivative against RL, for which you need to use, because this is a division, you need to use the knowledge that you have about derivative of a division, which is given in here. In fact, d by dx of v over u is v du by dx minus u dv by dx over v square. Using that you get this expansion or this derivative. You can do that at home and see how that becomes, and simplified like this, and this the denominator or the numerator, this part has to become 0 for derivative to be 0, because this is anyway not 0. So that's what they have done in here. They have equated this to be 0. However, ETH is also not 0, so this part what is inside that bracket, large bracket, square bracket, would be it would have to be equal to 0. You expand that, you get RTH squared minus RL squared equal to 0, giving you the result that RTH equal to RL equal to RTH is the condition that you need to satisfy in order to the for the derivative to be 0, meaning that that is the condition that you need to acquire or have in order to have a maximum power transfer to the load. Right. An example. Consider the circuit of figure 9 point, this one, right, and determine the value of load resistance required to ensure that maximum power is transferred to the load. Find VL, IL and PL when maximum power is delivered to the load, right? So we have to first find the Thevenin's equivalent for this circuit. So let's keep this Thevenin's equivalent for the circuit, which is, let's find it. Now first we need to remove the load, right? Once you remove the load, you will get the circuit excluding the load, that is sorry, that is this part, right? So I'm going to remove the resistors as well, rather the low the sources as well, and draw the circuit in here. So this is a short and this is an open, and you have a resistor here, and that's that. So this is 2 kilo ohms and this is 6 kilo ohms. We did this example, I guess, previously. Anyway, we will continue that. I don't think we need to continue, right? So this is our RTH is equal to RTH is equal to 6 parallel 6k parallel 2k, which is 6 into 2 divided by 6 plus 2 kilo ohms, which is 12 divided by 8, 1.5 kilo ohms. As far as I could remember, this is the same circuit we used in one of the examples in let's check this one and see. In this one we had that circuit, right? Let's give it a quick look and see. Oh no, it's different, one. That's the circuit, right? So that's the same circuit that you have, right? Yes, it's the same thing. So using the previous example, we can say ETH is equal to what was ETH? ETH is this, and ETH became 11.25, right? 11.25 volts. So now the Thevenin's equivalent is ETH and RTH is there. ETH is 11.25, RTH is 1.5k, and you have variable RL, right? RL. So this is equivalent, and using maximum power transfer theorem, maximum power transfer is when RL equal to RTH. So therefore I dot E dot, which is that is when RL equals 1.5k kilo ohms. The question, let's close this one. The question asked you to find out, okay, determine the transfer the load, find VL, IL and PL at this. So VL at maximum power, that was not written in the same line, right? Okay, maximum power transfer, at maximum power transfer, VL, the load voltage, that is VL, and this is IL. VL is, so you have a same resistance here, same resistance here, so that is half ETH, which is 1.15 volts, sorry, 11.25 volts divided by 2, which is 11.25 divided by 2 is 5.625 5.625 volts. At that point IL is 5.625 divided by RL at that point, which is 1.5K, which is this divided by 1500, which is 0.00375 amperes, which is 3.75 milliamperes, and the power P L is equal to VL IL, which is 5.625 volts into 3.75 milliamperes. So this into 5.625, so it's 0.021 watts, 0.021 watts, which is 21 milliwatts. So we have completed the whole question now. So yeah, so that's how we do that. Use the maximum power transfer theorem to find out the maximum power transferred, as well as the voltage and current, resistance values, everything under maximum power transfer condition. Right, so far we had all impedance sources, like all the voltage sources. We knew exactly the voltage or the current, all the sources, voltage sources, current sources were definite sources, so they actually were independent sources. If it was 5 volts, it was 5 volts, so there were no dependency on it. Excuse me. So now we look at what if we have dependent sources in a circuit. Now, what are known as dependent sources? We have actually 4 categories of sources. Now the dependent sources are, now let's say if it is a voltage source, like what we have shown in here, the voltage source, some other current or a voltage becomes actually controls the voltage of that particular voltage source, in which case it can become a voltage control voltage source or a current control voltage source. Now voltage control voltage source means the voltage of the particular source we are considering is controlled by another voltage in the circuit. Similarly, in the second case, the current, the voltage of the particular voltage source we are considering is controlled by a current in a different place of the circuit. Similarly, we can have current sources that are controlled by either a voltage of the circuit or a current of some other place of the circuit. So in that case, we will get voltage controlled current sources or current controlled current sources. Let's look at the case, like dependence. In this case, it's a voltage that controls the voltage of the source. This is the symbol of a control voltage source. Both these, in fact, and this is the symbol of a current controlled current source. And you can see the equation. This is a voltage equation that we have, meaning that the voltage of this is controlled by another voltage. In this case it's V1. Here it's a current that controls the voltage of this voltage source. Now this is a voltage source, but you have a current relationship, so that does mean that this current I1 controls the voltage of this. The third case is a current source which is controlled by a voltage of another place, and here it's a current source which is controlled by a current. Now in this case both are voltages, so this is a unitless factor. In this case the output, this is a voltage but this is a current, so it's a resistance value that you need to have as the constant in here. However, in this case the output is a current and the input is a voltage, so therefore this takes units of 1 upon resistance, the conductance. Conductance is the unit, or this is G is a conductance, 1 upon resistance. Here again input is a current, output is a current, so beta is a constant, unitless constant. Right, so the method that we have to use is, first we treat the dependent source as an independent source, right? You just treat it as it is with the equation that is given in there, and write the KVL equations and just apply the dependency. Dependency is this dependence. You substitute whatever the values that is given by the dependency equation, that is in this one, or this one, and this one, in the equation. So that will give us the solution straightforward. Let's look at an example. Find V out of the circuit. So that is this voltage of the circuit in here. Anyway, we'll take this out and that's easier for us, right? Okay, let's go to a new page. It's a little too small, right? Okay, this is good. So what we want to find out is V out. For that, let's say we apply mesh analysis, right? Now the voltage here is Vx. Based on Vx, that is this voltage. The voltage here is Vx. So based on the voltage Vx, this is dependent. So now let's look at how we can do that. What was said earlier is, okay, let's follow the same procedure that we followed earlier, right? We marked clockwise currents, so use mesh. Was that the question? Now we must find. Use mesh analysis. This is for mesh analysis and nodal analysis, right? So in this case we can use mesh analysis because both these are voltage sources. The second, this is I1, this is I2, right? According to the voltages that we have marked, we have plus minus, plus minus, plus minus, plus minus. Now ultimately if we find actually I2, we can find V out easily, right? Let's apply KVL, right? KVL to loop 1. We get here plus 2Vx minus I1 2K and minus I1 4k plus I2 4k equal to 0, right? This is equation number 1. For loop 2, KVL to loop 2, you get minus I2 4k plus I1 4k plus 3 minus I2 6k equal to 0. Now here, what is Vx? This is equation number 1. Sorry, equation number 2, right? What is Vx? Vx in this case is plus I1 4k minus I2 4k. Oh yes. Now equation number 1 can be rewritten as twice, right, twice Vx, that is I1 4k minus I2 4k, right, minus I1 2k minus I1 4k plus I2 4k equal to 0, right? In here we can actually cancel out all the k's, but before that we will try to simplify this. You have 8k minus 2k minus 4k, which is 2 I1. Here we have minus 8k plus 4k, so it is plus 4 minus 4 I2 equals to 0, so k can be cancelled out. So this is equation number 3. Let's say from here we get another equation, right, which is right, so 4 from 2, if you simplify 2, we get we'll push the 3 to the other side, so 4 I1, this is minus 4 minus 6 is minus 10. Okay, do we have 6 there? Yes. Minus 10 I2 equals minus 3. Yes, so we'll have to leave it as it is, so that is equation number 4. Now from equation number 4 and 2, what is D? D is equal to 2 minus 4, 4 minus 10, which is 20 minus 20 plus 16 equals minus 4. Then I1, I'm using determinant method because it's easier. Actually what we want is not I1, right, what we want is I2, so I'm going to write I2 straight away. I2 is okay, you keep this as it is, 2 4, but 0 minus 3 divided by D, right, so that is minus 6 divided by minus 4, which is 2, 1.5 amperes, right? So I2 is 1.5 amperes, so therefore V out is amperes, right? Oh, sorry. Yes, it has to be. Okay, so we'll have to keep the we'll can't actually cancel this out, so this will have to be 4,000 and this will have to be 10,000, right, because K's were there. In that case this is 4,000 and this is 10,000, right? In that case this is actually 20,000 plus 16,000, which is 4,000, right? So this here this becomes 4,000, right? In that case this is not there. This divided by 4,000, which is 1.5 milliamperes, right? 1.5 milliamperes. Therefore V out is I2 R3. R3 is the third resistor that we had there, right? So 6K, which is equal to 1.5 milliamperes into 6 kilo ohms, which is, right, million kilo cancels out, so 6 into 1.5, which is 9, right? So we get 9 volts there. So if you want to find out I1 is given by this 0 minus 3 and the second column minus 4 minus 10,000, minus 4 minus 10,000 divided by D, right? So which is actually, we'll find that as well quickly. Now in this question you don't have to find I1, but here we will find I1 as well. I1 is right, this minus 12 divided by D. D is 4,000, right? Minus 4,000. So 12 divided by 4,000, or let's say it is 3 milliamperes, right? If you want to find that. Done. Next. So that's all. So what you need to do actually is just simply now in this case what we did was we didn't bother about what this 2x is. We applied using this 2x directly, and later on we found a formula for Vx, and that was substituted. That will end up in 2 by 2 system. So it's the same case we have to do in nodal analysis as well if you have a dependent source, but this method is only for keep in mind please that this method can be used only for Norton, only for mesh analysis and nodal analysis with dependent sources. You can't use the superposition theorem and things like that when you are having dependent sources. Those techniques will be taught to you in the second year, right? So for now, if you have a dependent source and when you when you want to perform mesh analysis and nodal analysis, this is how you do it. Simply treat them as sources, independent sources when you apply KVL equations, and then substitute a value for the dependency, that is in this case Vx from other means, and then you will be able to simplify the system. So that's all for today, and let's meet next week or next time Next lecture will be on AC. So we will be starting, well, that gives a indication or good news that we have finished the discussions on DC analysis, DC circuit analysis. So we are in position now to start with AC analysis. So next lecture will be on AC analysis. So stay at home, be safe, but study hard. Good luck. Bye for now.